So let's start. Hello everyone. So the speaker for this session is Professor David Witt Nyström from the University of Gothenburg, who is also the recipient of the Frontiers of Science Award. Today he will tell us the story about duality between the pseudo-effective and the movable cone and projective manifold.
Yes,
please.
Yes, thank you very much. And let me start. So let me start by thanking the organizers for inviting me and giving me this opportunity to speak. And I should also warn you that there will be a quiz in the end, so you have to be very attentive throughout the whole talk. Okay. Okay, so the setting is this. We're gonna consider a compact Kähler manifold X. Okay, and then sort of given that there are sort of two natural vector spaces to consider. So we have the vector space of 1, real Dolbeault cohomology classes, and then the vector space of n-1 cohomology classes. Okay, so these are two finite dimensional vector spaces. Okay, and in those vector spaces there are some convex cones which encode some very important information about this manifold. Okay, so I saved some time here by already drawing it. But so in this H11 space, so first we have this red cone. So that is called the Kähler cone. So, and it consists of all classes that contain a Kähler form. Okay, and it's easy to see that this will be a convex cone, and it's going to be open. Okay, so then the bar here, it means that we take the closure. So this will be a closed convex cone. It's called the Neff cone. Okay, so and the class is Neff if it's sort of in the Neff cone. Okay, so that's the first, or the two first cones here. Okay, but then there's this somewhat bigger cone that I forgot to write it here. Okay. Okay. Okay, so that cone, it consists of classes of not necessarily containing Kähler form, but that contain some closed positive current. Okay. So of course, a Kähler form is also a closed positive current, but there are much more of these. So this would be a bigger cone. Okay, and this is called the pseudo-effective cone, or the PSEF cone. Okay, and then we go to the n-1 space here. So then we start looking at this thing that I've denoted by n here. So now this looks very similar like this. So we look at all the, it consists of all the classes which contain a closed positive n-1 current then. Okay, and that is similarly called the pseudo-effective cone. Okay, and then there's this fourth cone, M, and its description is a little bit more complicated. So this is defined as the closed convex cone generated by classes of this form. So we look at some modification of X, mu, okay, and there we pick as a number of Kähler forms, so smooth Kähler forms, so on X tilde. Okay, but then we can push forward that down to to X, and then this will be a closed positive current. Okay, but it might not be smooth. Okay. Okay, so we look at the thing which is generated by all such things. Okay, and that is called the movable cone. And the reason why that is called the movable cone is because if we imagine that these Kähler forms are curvature forms with respect to some line bundle. Okay, and then I mean, this line bundle will have to be sort of an ample, and imagine that the line bundle has sections. Okay, so then you will have these sort of hypersurfaces. Okay, and then so this class will be the same as sort of the class of these sort of hypersurfaces that you push down. So this will correspond to the class on X of sort of the intersection of these. Maybe I didn't explain it properly, but this will correspond then to a curve on X, and that curve will be able to move because I mean, these things will move upstairs. Anyway, that's the reason why it's called the movable cone. Okay, and now, so these two vector spaces are dual to each other by this Poincaré pair. So, I mean, so if you have two classes, I mean, just take some smooth representatives and you can integrate. Okay, and then it's sort of natural question, sort of how these cones sort of relate to each other given this duality. Okay, so the first theorem I want to mention now is that of Desmaillet and Paun. Which says that the Neff cone and the pseudoeffective cone are dual with respect to this pairing, which sort of more concretely means that a class alpha is Neff if and only if for all pseudo effective n-1, n-1 classes, this integral is non-negative. Okay, so that's what it means. Okay, so if we look at it, so actually, so the only if part here is obvious, because if alpha is Neff, okay, so if say alpha is actually Kähler, then you can sort of you take a Kähler representative, and then you take a closed positive current here, and then you integrate, and then sort of by definition this will be non-negative. Okay, so that's sort of immediate. So the hard part is the if part, to sort of just knowing. So if alpha is a class and you just know that sort of paired to any such beta, this is bigger than or equal to 0, how do we know that alpha is Neff? So this is the hard part. But then that follows from this deep result of Desmaillet and Paun about the numerical characterization of the Kähler cone, as far as I understand. Okay. So a little bit later, there was another result by Buxom, Demailly, Pound, and Peternel. Which said that so if X is projective, then we have another duality statement. And I will explain this very shortly here. So then sort of E and S and M and S they are dual. And now, so in the projective case, you can sort of, instead of looking at these these big vector spaces, you can look at the subspace sort of generated by classes corresponding to subvarieties. And those are called Néron-Severi spaces. And if you intersect these Néron-Severi spaces with these cones, then you get these sort of algebraic versions. So where this is simply this intersection. So if you're doing algebraic geometry, then it's sort of very natural to look at these sort of cones instead. Okay, so they prove this duality statement between sort of the pseudoeffective and the movable cone, but in the algebraic setting. Okay, but in the same paper, they formulate the conjecture that sort of on any compact Kähler manifold, we should have that the full pseudoeffective and movable cones are dual. Okay, so somehow completing this picture here. Okay, any questions? What? Yes, because yes, with respect to this one. Okay. Yes. Okay, and then so my result was then that well, at least if we assume that our manifold is projective, then these cones are dual. Okay. Yes. Sorry. Yeah, but they will be automatically also, I mean, but you understand I mean, if you know the closure, you can understand the interior as well. And the point is that it's supposed to round. Aha, okay, yeah, I mean, this was, so there might have they might have a polygonal part as well, Okay. Okay. Yes. So how do you see this? Well, so as I said here, so there's like one aspect which is sort of easy here. So so if if alpha is pseudoeffective and beta is movable, then you can see that this pairing is non-negative, and that's because you can take a close positive representative here, right? And then you can take a so you can take a class of this thing, and the point is that you can pull back a closed positive 1,1 current by simply pulling back the function, and the pullback will still be positive. So you will have so you can pair that with these smooth califorms, and then that will automatically be positive. Okay, so that's sort of the obvious part, and that's, I guess, the reason why you might think this is, might think this to be true. Okay, so what that means is that the pseudoeffective cone will be at least included in the dual of the movable cone. Okay, so we know one inclusion. Oh, yeah. Yeah, you have to use your imagination. Sorry. Okay. Okay. So how would you sort of prove the equality then? Well, so it turns out that sort of the key notion here is that of volume. If you have a pseudoeffective class, then you define the volume of that as, well, you can define it in sort of different ways here, but I will do it in the way which sort of serves sort of my later purposes the best. So I define it as the supremum of these integrals. So I take a closed positive current T in alpha, and then I want to take the top power and integrate, but you cannot really do that if you have a singular current. So I need to sort of integrate away from the sort of the singular part of T. Okay, and then this will be some number, and I take the supremum, and here, so I'm taking over all closed positive T in alpha. Okay, and then if the class isn't pseudoeffective, I just let the volume be 0. Okay, so this was introduced by Buxom, I believe in his thesis, and he shows sort of two important things about this function. So first, so if the class happens to be the first Chern class of a line bundle, then this volume that is defined here, it will be the same as the volume of the line bundle, which was introduced earlier, and which is defined in the following way. So you take the Lehm sup as k tends to infinity of the dimension, the dimension of the space of sections of L to the power k divided by k to the n divided by n factorial. Okay. So this is okay. This was done earlier in this algebraic setting. Okay, and sort of another key aspect is that you can see, so a class will lie in the interior of the pseudoeffective cone. So and you say that, then you say that alpha is big. So this is sort of true if and only if this volume is strictly positive. Okay, and this is important because this gives a sort of a way to check whether you're sort of in the interior of this cone. And sort of you need to do that when trying to sort of show this equality here, you will need to be able to tell that. Okay, so this means that sort of the volume can be sort of used in trying to sort of establish that. Yes?
So this volume is not, does not depend on numerical equivalence?
It only depends on the numerical equivalence. This, I mean, but that's a theorem that it only depends on the numerical. Sorry? No, but then it will be 0. Yeah, yeah. So, but it's a theorem showing that it only depends on the numerical, equivalence. Okay. Okay. So the volume will sort of help us to try to show this sort of equality. But sort of this is not enough. You need more detailed information about this function. And then we have this conjecture due to the MIE, which says that for all pairs of NEF classes, we have the following inequality. So the volume of the difference is bigger than or equal to the integral of the alpha to the n minus n alpha n minus 1 beta. Okay, and this is known as the sort of transcendental holomorphic Morse inequality. Okay, and the point here is that so in this paper. They showed that if you assume this inequality, then it implies the duality that we want. Okay, so I would like, I would have liked to sort of explain the argument, but it's a little bit too involved to have time to do. But it's a nice argument, but it sort of crucially uses then the volume and the facts, these two. Okay. Okay, so yeah, and okay, so and I also want to say so. So as you remember, they proved this duality in this algebraic case, and that they did exactly in this way, using the fact that if you assume that sort of these classes are algebraic, then it's not very difficult to show this inequality. Okay, because in the algebraic case, then you have a different description of the volume, and then you can use sort of more standard cohomological methods, and yeah. Okay, so that's sort of how their proof went. So really the only thing that is missing in the sort of transcendental setting is this inequality. Okay, so what I showed was I showed that the inequality sort of at least holds when the manifold is projective. Okay? Let's see what's. Okay. Okay. So I will sketch the proof, and then I'll see how much time I have left afterwards, if any. Yeah. Okay. Okay. So how would you prove that kind of inequality? Well, so the first is some observation that it's sort of enough to show a somewhat weaker inequality. Like this. Where so you can also assume that alpha is not only Neff but Kähler, so it sort of contains a Kähler form. Similarly for beta. But then crucially, because X is projective, here we can also assume that this beta is integral, so it's also the class of the current of integration along a hypersurface. Okay, and then we're also allowed to assume that the difference lies in the interior. Okay. And the key thing here is, of course, that we have this hypersurface. Okay. Okay, so what do we do with the hypersurface? Well, so then we can write. So this current of integration, it lies in the same class as omega beta. Okay, so we can write it as omega beta plus ddcg for some function. Okay, and now G will have this kind of logarithmic singularity along Y. So let me indicate it like that. And for reasons that will be apparent in a bit. So G is singular, but if I take some maybe large value R, then I can sort of regularize G. So I sort of do like that. So what this means that, so GR is a regularized maximum of G and minus R. So, and now this is a smooth function. And another important thing here is that it's going to be sort of PSH with respect to this omega beta. And this simply means that if we take omega beta plus DDCGR, then this is a positive form. Yes? Yeah. Okay, so now comes the sort of the key thing here. So we let phi of R be this kind of supremum. So we take the supremum of all phi bounded from above by GR. Well, all phi which are PSH with respect to omega alpha. So this is an envelope. This is an envelope construction which is very classical in pluripotential theory. And a key thing with these envelopes is that they are themselves then sort of plurisubharmonic with respect to this sort of reference. Okay, so and it might, well, it might look like this. So this is phi R. Okay, and two sort of important things to note here is that first, if we take this current that we get using the envelope, and then we take the top power, so this is not necessarily smooth, but it's sort of smooth enough so that you can actually do this. So you can integrate over the whole thing, and this will be the same thing as if we just integrated sort of that thing. So this is just the integral of alpha to the n. Okay. And okay, so and another important thing here is that if we, okay, so this thing, it's going to be a positive measure. Okay, but actually, and this is one thing which is extremely useful about these envelopes, is that you can say very much about these measures. In fact, it's going to be supported on the set where the envelope is equal to this obstacle. Okay, so you see here. So here there's going to be nothing. Okay, so it's going to be supported where these two agree, and then you can sort of naively there. I mean, phi r is equal to jr. So naively you would say, well, so it should be. You can just change it here. Okay, so but and the good thing is that it actually works, but it's not as easy as it looks, because you have to, in order to do that, you have to know something about the regularity of phi r, and that is sort of a subtle issue. But this was actually shown by Biermann some years ago, and then in this setting, and then there's now a more general result by Dinezza and Trapani showing that this is actually true in a great generality. Okay, so this is an absolute sort of key property of these envelopes. And now, when we know this, then we can do a very simple estimate because so what you can do is that you can just add this omega beta. I mean, it's a Kähler form. It's just going to be much bigger. Yes, it's very simple. And then this is then, I mean, and this is sort of positive everywhere. So you can sort of you can also forget about that thing if you want. I mean, the inequality goes in the right direction. Okay, and then now this is a sort of positive form, and so now we can sort of use the binomial theorem. So we can write this as okay. So and now, okay, so there's just one sort of idea left to use here. Okay, so so this works for any r. Okay, and now we let r tend to infinity. Okay, and then it's easy to see here that the phi r will decrease to something that we call phi infinity. This you see here, this is going to be bounded from above by G, sort of by construction. And the way these Puri subharmonic functions work is that this is also going to be sort of Puri subharmonic with respect to omega alpha. Okay, and then, okay, so then we can look. Then we can look at this current. Now, you notice here that so phi infinity is less than or equal to G. So it means that this current will have this kind of singularity along Y. Okay, so it will have like the long number at least 1 along Y. And then we know that, so that means that we can actually remove this current, and it's still going to be positive. So here we get the positive current, and we see here that this thing lies in alpha minus beta, which is good. Okay, now we're ready here. Okay, so now I want to estimate the volume of alpha minus beta. And sort of by definition here, the volume is the supremum of sort of all such integrals. So it's going to be bigger than or equal to this integral. Okay, yes. Now, okay, so this is the singular set of this current. Okay, so the singular set, it will sort of contain, or it might contain Y. Okay, it might also contain other things, but you can show, I will not say exactly how, but you can sort of show that actually the singular set will at least be small. So it's sort of in the I mean, it will have yeah, it will have like 0 volume. Okay, so I can take a pretty large set avoiding that thing, and I call that U. Okay, and this current sort of does nothing on U, so I can write it like this. So this is going to be bigger than or equal to the integral over sort of the closure of U like that. Okay, but now phi r converges to phi infinity, and it decreases to phi infinity, and then there's a continuity. I mean, so these measures they are sort of continuous with respect to these sequences. So this is going to be bigger than or equal to the limit of these integrals where I have phi r, okay, and now I use this classic trick of, so I can write the integral over u as, okay. So I mean, I can write it as the difference of the integral over the whole of x. Minus the integral over the complement. Okay, it's pretty obvious. Okay, but we know what the full integral is. That's just okay. So the full integral is, as I said, just this thing. And now I sort of use this. Now I use this this inequality, and I integrate over the complement of u. Okay, so I get then minus over k. Okay, but now you see here, so the inequality, I mean, I can just, it just gets better by integrating of the whole of x. I mean, it just gets better. Right, and now sort of these things is nothing but these numbers that I had before. And I said that I can actually make, I can sort of make the complement of u arbitrarily small, sort of in this, say, in this sense. So I can actually assume this to be negligible. So it's sort of, this is going to be approximately 0. And then you have it. Okay, so maybe I've already run over time. I haven't kept track of the time. Okay. Okay. So this is okay. So this is the proof. I haven't said anything about sort of the, I mean, applications or why this might be useful. So I mean, the thing is that it is actually useful. I don't have time to sort of go into it very deeply, unfortunately, but it has various consequences on. I mean, even if you, so you don't, even if you're sort of only really interested in Kähler forms or Kähler classes, this actually has consequences because it tells you things about how Kähler manifolds can deform. So I just want to give you very quickly a sample sort of application. Not of Okay, so it's an application not actually of this theorem, but a slightly stronger statement. But it's sort of very, very much related. Okay, so so you can prove, for instance, prove this thing, which I don't know, I thought was interesting. So if you have a say that you have a compact Kähler manifold, then for all positive epsilon, you can find some Kähler form in the same class as the given one, and a Kähler embedding sort of into this. So where so E is an ellipsoid in Cn. So and this is just the standard Euclidean Kähler form on Cn. Okay, and such that sort of the embedding captures almost all the volume of X. So okay, so you so here's X, and it's sort of the large part of X really looks like a standard ellipsoid. Okay, so it's just an example that sort of these kinds of things tells you sort of what kind of Kähler metrics sort of you can find. Okay, so I'll leave it at that. Okay.
A very nice talk. So, any questions or comments?
Sorry, it's related. Yeah, it's very much related. So because you always have, I mean, you always have approximate Zariski decompositions, but this is like a quantitative version of it. So you really need some very you need some strong control of how good sort of the approximation is.
And what does this ellipsoid mean in algebraic geometry?
Oh, then in okay, the ellipsoid. Yeah. So this okay. So this I mean, this was just one example. So this is say connected to if you want Ukunkov bodies. Yeah.
Okay. Thank you.
So, any more?
Just about the definition of movable cone, is it possible to avoid the solution, the block, project setting this definition?
I mean, yeah, it follows. Okay, so it follows from this that actually the movable cone is the same as another cone, which has also been studied, called the balanced cone, or maybe it's a closure of the balanced cone. Okay, so and that has in a way a simpler definition, because it's just smooth positive n-1 forms. You need my theorem for that, and I think actually that somehow you actually want the connection to the modifications, because what's interesting is well, from my perspective, so really what's interesting are these modifications. You want to have some information about these modifications. So at least for sort of define the kind of applications that I'm interested in. So I think actually, I think that so what you're really interested in, the behavior of this volume function. That is sort of the key, rather than the duality statement. And the point is that sort of, and you want information about the volume because this is connected to, I mean, the sort of modifications of your manifold, and you would have seen that maybe better if I had used the other definition of volume. Yeah. So there are easy so you can sort of define the movable cone sort of more easily, but actually it misses the point a little bit because actually the connection to the modifications are sort of what's most interesting about it. It was a trick. I just wanted you to be attentive.
So, any more questions or comments? So maybe I have one. So your X is a projective manifold, right? So how about the duality phenomenon in like singular case? If you allow X to have singularity, I mean maybe mild singularity.
I'm sorry, you're asking the wrong person.
Oh, it's fine.
Yeah.
Okay.
Yeah, so I think, I mean, Mihai is probably a good person to ask. Yeah.
Okay. So any more questions or comments? So if there are no more questions, let's thank the speaker again.